Any comments for the good of the order before we get going? I guess you don't care about your assignment yet, because that's not due in the next 8 hours, 4 hours. Do I lie? No, I don't think so. So, yeah, fine. So, presume you got your stuff in fine last time. All right, well, maybe we get going, and people will arrive when they arrive. Oh, that's inside. Where's the... All right, so to kind of bring us up to speed, everything we've talked about so far is encapsulated, I'd say, on this figure. We've talked about it many times. You're quite familiar with it by now, I think. That we have these two relationships, capillary pressure versus saturation and relative permeabilities versus saturation. We know, I think, how to use both of them. The top one says something about the role of capillary forces in controlling saturation. And when we talked about solving numerical models that address these multiphase flows, the fact that we have to solve 2 equations to close the set of 4 equations for 4 unknowns. And the 2 closing equations are that saturations add to 1, and that the capillary pressures in the 2 fluids must be conform to the capillary pressure saturation curve. So that's our reason for doing it. Our motivation was much simpler than that, though. I think it was to use this capillary pressure curve to scale pressures with saturation, so we could use them with elevation above the water table and with depth below the water table for NAPLs and for air and NAPLs alike. We noted the hysteresis, we noticed an entry pressure, a bubbling pressure. We noted that this was equal to 0.3 in terms of this Leverett function, which is non-dimensional, where we typically can easily get permeability by measuring it, can easily get porosity, can easily get interfacial tension, but can't very easily get bubbling pressures. So this is a easy workaround to be able to do that. So we can get a value of the entry pressure at 0 saturation, which says when we start to invade with another fluid. And this represents the behavior of a capillary barrier. This is the clay layer, which has the puddle of red NAPL sitting on top of it, is because it can't get entry. It needs a much larger pressure than this to get entry. So that's the reality of that. We talked about relative perms, the fact that something on fire. Am I having a stroke again? That they are hysteretic and they have different heights based on the big pore spaces filling. And we finally did a bit of mental gymnastics to derive exactly why the bubbling pressure is given by this J function equal to about 0.3. And the fact that the scaling is uniform. So if you have a curve that looks like this, and an intercept for the bubbling pressure for one fluid and a porous medium, you could calculate what that would be for another fluid, which I think is the exact topic of your assignment number 3, but I can't remember. And so, ears perk up. You're so predictable. So, yeah, it is. I think you have to create one of these capillary pressure versus saturation curves and then say what the behavior would be for gasoline versus TCE. And so you can rationalize how to scale that based on this magic behavior. And finally, what we use them for, we've used them to be able to say something about the distributions in saturation in the vadose zone, where the capillary pressure is given by the difference between these 2 pressures, air pressure, which is roughly constant as you go vertically because of the unit weight of air is so trivial, and water pressure, which is not constant as you go vertically, which pressure reduces as you go up. So if it starts off the water table at 0 gauge pressure, then by the time it's up here, this is negative. And so by definition of capillary pressure being equal to pressure in the non-wetting minus pressure in the wetting phase, then the wetting phase is negative, tensile, and so this capillary pressure is positive on this limb, as you know from this. So even though it looks like the water is in tension, because by definition the capillary pressure is the non-wetting minus the wetting, and this is the pressure in water, negative negative is a positive. And so this is the capillary pressure is going up. So it allows you to define the saturation as you go upwards. This would be the saturation of the non-wetting, and this would be the saturation of the wetting. 100% saturated when it's at the water table, capillary tension saturated zone, so this is in tension, enough tension to keep it completely saturated, essentially, and then how these change. So this is air water, and this is NAPL water, and specifically DNAPL, right? Because it's below the groundwater table. And so we'll talk about these things today for NAPLs. But this also is controlled by capillary pressure. So as you go down in depth, now the water is in compression and increases with depth, but the non-wetting fluid pressure grows faster because it's denser, maybe 1,600 kilograms per cubic meter instead of 1,000. And so again, the capillary pressure is given by this equation. The water is in compressive, so it's positive. But the non-wetting is also positive, but it's larger than the wetting. And so it's the difference between these two curves. It just happens that it's capillary pressure is positive in each case. And that means as you go down in depth, then these are the distributions of the saturation of the non-wetting, just like it was here. The only thing that's different is that the non-wetting is an apple, and the wetting is water. And here it's the non-wetting was air, and the wetting, because it's the same reservoir, is water. Okay. So that's everything we've done so far, kind of in a nutshell. And that's why we've done it, so you can get distribution of saturation. So let's talk a little bit today about what we expect these saturations to look like, both in the vadose zone and in the below the water table, from a maybe a more practical standpoint, using some observations from laboratories and field testing sites, among others. Okay. So I'm going to switch from this to this. Something smells good. Don't know what it is. What is it? I don't worry about people bringing. Those are administrative rules. No food or drinks inside. I guess they're a practical rule, right? Practical rule is you don't want to spill it over the seat for the next class to come in. So I can get with that, but otherwise I don't care. You have to realize the reason for rules before you break them, right? Don't you believe that? Come on. You've got to be reactionary. Anyway. All right, that was our recap. So we'll talk today about both NAPLs. And we'll talk both in terms of LNAPLs and DNAPLs and their different behaviors. And so it'll just be, we don't need to talk about that. The gradients of pressure that you can apply to try and move these things by dragging a blob of a DNAPL or an apple by viscous forces on it are so high that you'll never move it. So we don't really need to think about that. Once they get locked in by capillary forces, then we don't have to worry about them moving. The only way we can get them out is by contacting them directly in that phase and sucking them out, or by dissolving them, or by vaporizing them by heating up the aquifer, the subsurface reservoir aquifer. And so if we look, first of all, at the capillary pressure versus saturation relationships, what we're trying to represent is this behavior. We've had these cartoons before. These cartoons for us have had a water table where the water pressure is atmospheric. Above it, the tension saturated zone gives this zone 100% almost saturating the porous medium, but at liquid pressures which are less than 0, negative. And if you spill gasoline onto that, we expect this little lens to form because the lens is buoyed by the water that's underneath it. It depresses it because it's able to apply a pressure to it, which is the weight of this free product acting on this portion here. Originally there's no weight acting on it, but once this comes down, this is acting, so it pushes down the water table in this zone, and it leaves a smear as it goes through. If there was enough liquid to keep this saturated, then maybe this chimney would be more saturated than just a smear, but we know that this can be present at the irreducible saturation of the non-wetting fluid. So we'd like to maybe rationalize why we get this architecture and link it directly to these capillary pressure versus saturation curves. If we look only at water and air in the vadose zone, then this is what we've just talked about. This is these are the saturations as we go up, 100%. So this would be the irreducible saturation of the non-wetting fluid here, this small amount here. This is as saturated with water as it can get. This would be at the groundwater table, by definition, 0 pressure, gauge, atmospheric pressure you're feeling now. And this pressure in the liquid would be in tension, because we know that as we go up from here, the water pressure is like this. This would be pressure, this would be 1, this is a unit weight of water, and this would be elevation. And we'd expect to see within here the different components. So we know that this is going to be now, so this is waiting for air to break in through here. Air is the non-wetting fluid. So this would be the saturation of the non-wetting. And this would be the saturation of the wetting, the water that's left in it. In this particular figure, this is out of Feder. It's denoted, not donated. Donated as funicular zone. So you remember that funicular zone would be grains, which they were stippled for us before, I guess, or cross-hatched before. And so the funicular zone would be a bubble of air sitting in a whole bunch of water. In our previous figures, there's a little black dot of oil that was floating in a sea of water. But here, air is the non-wetting fluid rather than oil. And so this would be, by definition, funicular saturation. The corresponding pendular saturation is you have is the grains that contact each other. See if I can draw that. And those are each covered by a monomolecular, I should draw this, a monomolecular layer of water. And at the joining between these layers, we have this meniscus, this pendant of water. Goes around it and it goes across grain to grain. So that's present at these point contacts between grains. And so that exists here. So just now the bubble in here that's evolving is the air. And as the air grows, as you go from the right side to the left, So the saturation of the non-wetting fluid grows as you go that. Then more of this space becomes bubble. So the bubble grows until it essentially excludes the water, and then you're left just with these pendular rings. And so that's entirely logical from what we've talked about. And we can get the saturation of water as we go up from here. It should conform to the capillary pressure versus saturation curve, where instead of defining it in terms of this vertical axis can be defined in terms of capillary pressure, but it's also equivalent, I guess, to elevation. Because we know that capillary pressure doesn't want to write. Pressure in the non-wetting minus the pressure in the wetting. This is air, this is H2O. And we can merely write those as equal to the height multiplied through by the density of the non-wetting fluid minus the density of the wetting. Non-wetting fluid is essentially 0. Yeah. So capillary pressures, I guess all I'm saying is you can scale the axis by writing the axis as being equal to PC over these are densities, not pressures. Probably can't tell the difference, right? Just rewriting this. So this is just a scaling. You can write it in terms of the two pressures. You can define each of those pressures individually in terms of a height and a density. And so by definition, you can link capillary pressure to this. So you can scale this either as pressure, capillary pressure, or an equivalent magnitude of elevation. So, as you know. Okay. So what happens then in the vadose zone if you spill something like, I suppose, gasoline from the surface? Physically, what would happen? What do you expect based on what we understand about the mechanics of this? So this is also taken out of Federer's book. I'll make it slightly smaller so we can get all the things on the page at the same time. This is the same capillary pressure versus saturation curve. It's now written in terms of an elevation directly. And these are actually measurements that are made by having pressures measured in a column in the lab, I think, in this particular case. 70 centimeters tall, 2 feet and a few inches. And they define I think, a porosity. So we define saturation of water as equal to the volume of water divided by the volume of the voids. Volumetric moisture content, which is what these are given in, is equal to the volume of water divided by the total volume. So total volume is the soil and the voids. So in other words, if you have something that looks like a little cube of rock, and you could centrifuge it down so that you had the volume, it's going to be too small, but the volume of the voids, volume of the solids, and the volume total would be this whole thing. So not volume, so this is quartz, the volume of quartz, the volume of voids if you could centrifuge it down, and the volume total. And so all, perhaps a long-winded way of saying that the way that soil scientists define saturations as volumetric moisture contents, oil or water contents, is by volume relative to the total volume, not by the void volume. So if you've completely filled up the void space with this, then the saturation, so S max equals 1. Phi max equals porosity, which we've called N before, right? So when it's maximally saturated, all the void space is saturated, then the volume of voids will be, volume of water will be the volume of voids, and the volume of voids divided by the total is our definition of porosity. And I think you also need these for assignment 3, as I recall. So useful that we're talking about them. So in this particular case, the maximum water content is this. So it seems that in this case, maybe the porosity is equal to 38%, just from scaling here. This is the maximum. So this is the amount of the pore space which is still filled with air, and this is the amount which is filled with water. So this is H2O and air. And these proportions continue as you go up here. And so as you go further up in the column, as predicted by the capillary pressure versus saturation curves, the volumetric content of air and the volumetric content of water change. I suppose we could also note that the volumetric content of water plus the volumetric content of air must equal the porosity. This, right? Makes sense. If there's nothing else in the porosity, it can only be comprised of these two volumes. They're both normalized relative to the total volume, and so if you fill them both up, that would be definition. And all that's happening in this particular case, this experiment, is that you jump in gasoline into the top of this column. I don't know what it is. It's probably a graduated chemistry cylinder, 6 inches in diameter and obviously 3 feet tall. And you pour gasoline in the top and you measure how the changes in pressure and saturation occur. So these could be measurements of pressure that correspond to these elevations, and also measurements of water content. So as you push this thing in, then you get this little plug of, I guess we've done it as a green thing. Don't have green on this. Here's green. So this is our apple going in. And so you see this little nose down here and this coming up here. And so I suppose if you were to actually put in the different saturations on this, they would be just along this line, just a convenient line. This would be air, this would be oil, and this one that you can barely see would be water. So originally at 60, it was maybe slightly larger, but it's kind of squeezed out. It's added oil to that section. It's taken away from the portion which was air-filled, and it's also squeezed down the water. And so this is, at the beginning, this is 2 minutes, 2 hours in, I guess, 120 minutes. This is 8 hours in, and this is the progress. We made the point before that this architecture that you get occurs within the first day, week, month that's going on. So that's kind of, this would be the same scale as a vadose zone, roughly. And so these are the time frames that you're looking at. This would be 8 hours, right? Less than a day, a working day. So this keeps on going down, and as it goes down, it starts filling it. And so now, if you take a section across here, then you can do exactly the same thing. This is air, this is oil from here to here, and this is water. And then finally, its resting point, which I guess is the main point of what we're talking about, is the QED, quo-weight diamostrandum, right? And that is, if you take a section through here, again, this is the same. Air, oil from here to here, and water. And so if you drew that on our water table, this is kind of what it would look like. No, not that. Look like this. And I guess it would be stuff here. And I need a blunt object to represent that. That would be this. It's not very blunt. And so if you think about going down through this particular zone, I guess this here, then this capillary pressure curve is really, with elevation or with capillary pressure, this is defining what those saturations are, or volumetric moisture contents, right? This puddle that sits on top of the water table, it's buoyed by the water table. What it's done is the water table started off higher and it's pushed it down because it has the weight of a liquid sitting on it rather than just a gas on it before. So that weight of liquid is what's pushed it down here. And as the water table has been depressed, it's forced this puddle to sit on top of it. And that puddle exists at a pretty big percentage. It's probably taking up 80% of the void space just looking at this. So maybe this volumetric moisture content is from 0.08 to 0.32, which is 0.24, is it? 0. Yeah, 0.24. But perhaps it's more convenient to think about it in terms of saturation. So the saturation would be 1 from this point to this point. So in terms of saturations, saturation of air is 10%. Saturation of oil is this length here, 80%. And saturation of water is about 10% as well. Right? Perhaps, yeah, about 10%. Air and water looks the same. Perhaps they're 15 and 15 and 70, but you get the picture. So that's really explaining exactly what we had in the subsurface. For obviously for an LNAPL, right? Because it's being buoyed by the water table. So this is an explanation of that. We could represent these as we did here in terms of saturations or volumetric moisture volumetric contents. They're both volumetric, just that one is referenced relative to the void volume saturation, and one is referenced to the total soil volume of a cube of soil. That's the only difference. They're both volumetric percentages, and they are saturations. The other thing that we know is that as you go higher up in here, this elevation is a unique function of capillary pressure because of the relationship that we just defined here, right? They're related to each other. So you could also get the capillary pressures and how those change with elevation as well. And so they'd be congruent with what we've just done. I don't know if it's the same experiment, but the sequence now, just to confuse you, is from A to B to C to D, so it's not vertically arranged. But the same deal. So now you start off with the section with these pressure measuring gauges in, tensiometers. T is for tensiometer, because it measures tension in the water, negative values. This is in pressures now, and it's in centimeters of water. So H would be equal to pressure in the water divided by the unit weight of water. So in a length, it's not a pressure, it's actually in a length. So by definition it's this. And so if you can measure these somehow, then in the starting point you start off with the water table, which by definition is at atmospheric pressure. So this in gauge pressure is 0. And as you go up in the water above that, the pressure in the air phase is 0 essentially, but the pressure in the water phase is negative in tension. And as you go below the water table, it's just a continuation of this. So this is 1 over unit weight. Actually, it's 1 over, and unit weight just from this is equal to PW over H. Right? This unit weight, this units are length. So it's actually, you need to substitute for this and change it around, but you get the picture. So you dump the gasoline in. It's still lighter than the water. So now you get this little nose of gasoline, which has atmospheric pressure at the base, and it's come down through the system to rest on top of this capillary fringe. The water distribution in the liquid column, the water column, is still the same as it was, unit weight, but now it's putting pressure on the top here. You allow it to continue, and this nose slowly just settles down. And so now, I guess you don't really know, you're just measuring these pressures in these components, so you have to surmise if you measure these distributions of pressures without knowing what the fluids are and without knowing what these lines are that you can put a straight line through these, and you can put a straight line through these. I won't leave that there. And you have to surmise what's going on. You know that if you put gasoline on it, the place where there's 0 atmospheric pressure by definition would have been the water table, but now it's the oil table. Same definition of a water table. Water table is the point where the atmospheric pressure is atmospheric, where the pressure in the fluid is atmospheric. This is where the pressure in the fluid is atmospheric, oil table. And below that, you have the pressures we could surmise are in the water, and where that actually hits the 0 pressure mark, that by definition is the water table. So you have an oil table and a water table sitting on top of each other. And the pressures in the oil table increase according to the unit weight of the oil, gasoline. It should be, I guess, steeper slightly than the water because it's less dense, it's floating. Maybe 800 kilograms cubic meter, I think, something like that, instead of 1,000. So this slope should be closer to the vertical axis, more, but you can't really see it here. And this defines this behavior. And so that's maybe kind of a curiosity, but it's actually a bit more than this because it means that the oil will sit on top of the surface, and we'd like somehow to be able to measure what that looks like. We think from this figure on the left-hand side that we have this chimney, which is this smear zone, which we know from these previous figures should be at pretty low saturation. Might be irreducible saturation, might be a bit more, but pretty low saturation. We have this portion at the bottom which sits at almost fully saturated. So that's exactly the picture we have here. This is our lens of liquid. It's pushed down the water table, which was at this, the top of the capillary fringe was here. Now it's depressed it slightly. This is probably close to 70% saturated with gasoline. This might be 15% saturated, 20%. And this is depressing it might depress also the water table here below. And any contact of fluid which flows past this is able to pick up something from here and carry it down as a dissolved plume downstream, which is the mechanics of what's going on. So this kind of cartoon of what we've dealt with before is exactly borne out by this behavior that we now understand is going on in the subsurface. So one question we might want to ask ourselves is how much stuff is locked up in here? How do we know when we're successful, if we're sucking stuff out, if we're able to? We should be able to suck it out because it's present as a free phase. This we might not be able to suck out. If you suck on this, then probably you'll get air out of it because the majority of the phase is air, right? Most of it. So if you put a tube in here and suck out, you'll get out air. If you put a tube in here, you're likely to be able to suck out an apple. And if you go below it, it's water that you get. So you need a continuous phase to be able to recover it. So that's the question we might want to ask. So to do that, then we could think about drilling a hole. And so, 50, plenty of time. So to be able to get the picture for your nice assignments that you're sitting in a field and you know what's going on, that has to be got somehow. Typically you drill a hole. And the question is, how do you measure exactly how deep this puddle might be in the subsurface, because you can't see it. So the only way you can do it is to know where it rises to in that borehole and where the water gasoline interface is below that. And that would give you a thickness of product which you could use to make that calculation. But the interesting thing is, from what we've just talked about, is that we know that we have this pressure nose of gasoline sitting on top of the water, and there's a water table in there below the oil table, and we have to reconcile exactly how we could get that information. If we knew, for instance, in going down that this was really the top of the water and that this was really the top of the oil, then we immediately have a height, which I think I'll call W in the next part, just to be consistent. Let's just, yeah, called double. And if we knew exactly what that was by being able to measure it in a borehole, then that would be great. The problem is, if when we put a borehole down, the width of the borehole is so wide that there are no capillary effects in the borehole, but there are capillary effects in the aquifer. And so we have to accommodate that. So perhaps I'm making it more complicated than it needs to be. But this is the picture. This is the cartoon of what we might expect it to look like. The natural system is the LNAPL in green overlaying the water. The water has a water table and an oil table on top of it. The water table is at atmospheric pressure, and as you go above it, it's less than atmospheric pressure. As you go down in the oil table, it starts off at atmospheric pressure, and the pressure builds. So it's happy to do that. So if you could go into the aquifer and measure this top here and this base here, that would be great. You'd have your solution. But when you put a big hole through it, then all of a sudden this hole doesn't separate these based on the capillary forces at this interface. And it just allows them to mix like in a salad shaker. And so now what will happen in the well bore is the gasoline will flow into the well bore from the side, and the water will flow into the well bore from the side, and they'll reach some kind of equilibrium within there, which isn't necessarily the interface which is in the aquifer. I guess that's the point I'm making. And so you can again use marvelous fluid mechanics and statics to be able to reconcile that by saying that within this borehole, the interface, the force acting down in the green fluid has to be the same as the force acting up in the water because they're in equilibrium. And we can define each of those. They have to be the same at that interface. The pressure in the oil has to be the unit weight of gasoline, the thickness measured in the borehole, and gravity. The pressure acting up in the water has to be the unit weight of water, the density of water, the depth of water below the water table, and gravity. We know at the water table, by definition, the atmospheric pressure is acting. And as we go below that, from these figures, the pressure increases from atmospheric according to this. So that's all we're using. We're doing that. And so we know that that's the case. If we know that this is the case, we can equate these two. And if we equate these two, we get a result which is this, final result. And that is that the distance of this interface in the wellbore below the real water table, so this erroneous distance, a spurious distance perhaps, is given by W, and we can calculate that by knowing what the ratio of those two densities is. That's it. So this is where the interface should be if no capillarity exists, and of course no capillarity exists within the wellbore because it's too wide. And so now you can go in, you can measure the depth below the water table. You put a doodad in the hole to be able to measure where that top is. You measure, hopefully, where this interface is by having a special instrument to do that. And once you have this thickness measured, if you know what the densities of your two fluids are, then you can calculate W, bless you. And if you know what W is, you know what the true thickness is, which would be this. I don't know what we're going to call it. We can uppercase H is equal to measured T in the borehole minus W. You measure this, you calculate this, Bob's your uncle, you got it. That's it. That's it. And so now, this is the free product, right? So above this, we'd have our chimney of stuff that's come down through. We're not talking about this. This is our puddle that's sitting on top of, buoyed on top of the tension saturated zone. The volume of free product, as we say, this is what we called H, uppercase H. If we want to calculate how much pore space there is, and we have the puddle occupies the aquifer, which is of area A times H, right? So this is the green puddle. This is this over an area. So the volume of pore space is the area, the height of the green puddle, including the solids, but multiplied by porosity, so you only get the void space. And the volume of product can only occupy the pore space, but it's limited to the pore space minus the irreducible saturation of water, because it's left with water in here. So within here, you've invaded a previously wet space, and so it will only get as much water out down to the irreducible saturation of water. So this is the amount of product you'd have in the system. So an easy calculation to make. And I guess if you wanted to calculate recoverable, volume would be, if this is VT, let's call it VP because we've used VT before. VP, the recoverable volume would be equal to the volume total times 1 minus this is the oil that's left, gasoline that's left in the aquifer because it doesn't come out. Or you could rewrite this, this is the volume of product that's in there. The amount that's recoverable would be all this amount that's in there minus the stuff that stays in because of the water. Yeah, because there's just saturation. Okay. So this is kind of what it looks like as you go down. So we have these changes in saturation or volumetric moisture content as we go down in the system. And so we can approximate at least this zone here in terms of its height, calculate its measured height based on the real depth in the wellbore, the borehole, and correct for that. And we can represent this distribution in the subsurface that would look like this. So in the upper reaches, this would be what the air would look like. This would be the part that's that's oil filled from the oil going down here. This would be the water that's already in the system all the way through above the water table. This is the tension saturated zone. This would be the oil as it sits on top of the water table, and this would be the air that it would trap above this zone as well. So it gets kind of complicated, but not a bad estimate of that is just this simple way of looking at it as you go down in terms of these irreducible saturations. And I guess this is that same recoverable product that I wrote here, just defined here, with this extra term added. Okay? So one reason for thinking about how these could look is that you can do something much more sophisticated with this. And you recall that we had capillary pressure curves that we've said we know look like this in terms of capillary pressure versus saturation. Right. And you know that we could change these to look like log capillary pressure versus saturation effective. Right. These were log values. So we said that we could convert these curves, exactly the same data, by defining an effective saturation, which cuts off this portion here that we don't need to worry about. And if we do that, we can represent capillary pressure and saturation in log-log space. These same data, exact same data, but it ends up being a linear, not curve, but a linear distribution that we can represent by the so-called Brooks-Corey relationship. The reason for doing this is that you now have a nice relationship that defines capillary pressure in terms of saturation, and now you can look at the distributions of those behaviors both in the air gasoline and the gasoline water parts of the curve, and you can combine them in some way to say exactly what this distribution of saturations would be as you go through. So I won't subject you to that because I don't think it's particularly useful, but this comes out of Fetter and it just does that. The end result is kind of something that looks like this, also out of Fetter. And if I make it a little smaller, I guess I've marked up on it more than I really wanted to, so I'll choose a different color. So this is the a well bore that goes through it. This is the water table that sits in situ. This would have had the tension saturated zone. This would have been the water up to this point, then air water above this. This is the borehole that has the free product sitting in the borehole that goes down below the water table by some amount. This is what we called W in our case. And I guess this total amount here would be what we called uppercase T, the thickness that you measure in the well. And as we go up through the system, just to make the case that we'd expect from these arguments of capillary pressures both between the oil and the water and the oil and the air, we could comprise some composite capillary curves that would look like these two-shaped composite curves as you go up, which would define the distributions of saturations. As you get close to the water table, the gasoline is coming from the top and pushed down. So this amount here is oil in saturation in this particular case. So it's a big, thick puddle that sits here. This is water. This would be oil. And as you go up here, we're way above the water. And the two components as you go across here would be, actually three components. Right? This would be air. This would be oil. And this would be water. So not particularly important to get there, but to realize that our picture, simple picture of what we had here isn't perhaps that simple, a bit more complicated than that. But this actually isn't a bad representation of it using these estimates, because these other data are pretty tough to get, and so it's not very easy to get this figure. And so this exactly gives us this behavior. Over time. Let's take a break from that. So how do we get that? So
this is a short description of an LNAPL fluid system developed by flexible liner underground technology. An LNAPL fluid system was developed to detect pure product LNAPLs and DNAPLs above and below the water table in soils and rocks.
So the good thing for you guys, if you have to go out in the field and do things, I guess your jobs don't get taken by AI. So you should take some solace in that. So this is typical entry-level job is to go in the field and take samples and pump fluids in and pump fluids out. So this is a system, it's a direct push rig, so it's pushed down a certain depth. And now they line the open casing that's in the hole with this pajama pattern liner. And perhaps I'll put the volume back up. Why did the volume go down? Did I turn it down?
Below the water table in soils and rock. An LNAPL fluid system is a simple and cost-effective technique for mapping NAPLs.
This is one way to do it.
Color reactive cover for detection of pure product. In one application, a compressed NAPL flute liner is inserted into push rods. Water is injected into the liner as the rods are pulled, causing the liner to dilate against the whole wall. If there is pure product present, it will make a stain on the color reactive liner. When the liner is inverted out of the hole, there it is. Laid out on the ground, you will be able to map the exact location and depth of the contamination with the tape measure. Here are the 5 simple steps for installing an LNAPL flute color reactive liner using the direct push method. Step 1, push the rods to depth.
Why not?
Step 2, install the LNAPL flute liner and fill the annulus with water. This liner is going down very easily. Once the liner is in the rod, water is added to the annulus. We do this to keep the liner from dilating in the rod before the first rod section is pulled. Step 3, raise the rods one section and inject the water to dilate the liner in the hole.
So pull out the rods.
That's good.
You inflate it like a balloon so it contacts with the wall of the stuff.
Step 4, inject the water and then raise the rods. Repeat step 4 until all of the rods are removed.
Yeah.
Injecting to fill the liner, the other section of the hole wall.
Yeah. Fine. So the obvious, not obviously, but perhaps the part that you'd see there and sample would be exactly the same as the part we've just said. What you'd measure would be T, because it's in the borehole, not in the, even though the borehole's going through the aquifer, you're measuring it in the borehole. So now you need to correct that thickness for the relative difference between the densities of the fluids to be able to subtract this off. So you measure T, you can calculate what W is, and T minus W is the depth of this puddle. It's basically what it is. So the other ways to do this, I guess, has anyone done this? Been out in the field to measure? You measure the depth of water, you just put you can put a steel tape down, and I guess that's what is being done here. Very
Keys to access the well, a pipe wrench, steel tape, blue carpenter's chalk, they keep in the well, photo, or bag, used to estimate the hold point of submersion. Step 5, lower the weight and tape into the well until the lower end of the tape with chalk is submerged.
Yeah, I've never done this, but you rub chalk on a piece of steel tape, you put a weight on the bottom, you drop it into the well, You put it down, once it's been in the well, when it's contacted with water up to some level, it's taken the chalk off, and the part above that still has the chalk on it, so you get a well level directly from that. So I've never used that. It's much more common, I think, to use an electric, so-called electric tape, right? So, which is
And 200 feet
is this.
of the electric tape.
So,
DNA for electronically recorded of the electric tape.
so all it is a piece, two conductors with a tape between them. So just think of a tape with a conductor down either side of it that goes down to a little sonde the size of a finger at the bottom, and the conductors are separate except for where they come together at a little point in this sonde. And so when you drop this sonde and it hits water, it completes the connection, and either a little buzzer or a little light goes on this, so you know that you're at the depth of water. That's it. So pretty
DNA for electronic well with a pipe wrench.
pipe wrench. Have to.
On the indicator scale, light intensity, or sound, so that make sure that all readings are made by using the same deflection point on the indicator scale, light intensity, or sound. So
Not rocket science. You only have to do it once to know how to do it 1,000 times.
Slowly into the well until the indicator indicates that the circuit is closed and that the water surface in the well is contacted.
You might not have the luxury of only being required to do it once, but.
At the measuring point,
And I guess while we're here, sampling. We haven't talked about sampling. We don't need to talk about sampling now. But typically for wells, you'll bail them. You can lift it by dropping a hose down or a tube down and applying a nitrogen gas cylinder to blow the sample out of the well or raise it out of the well. But the other more usual way is to use a bailer, which is a bucket which you're putting into the well, but happens to be slim enough to be able to go into the well. And the only thing to note is, we'll talk about it in a second, is it matters how the bailer fills. So you could imagine this being sealed at the bottom and then filling at the top by going below the fluid surface and filling by decanting into the top. But some fluids will only sit at the base of the water, DNAPLs you'd expect. So some bailers will actually have a ball valve at the bottom, so that when you push it up, this ball valve floats and allows water in through the bottom. And then when you yank up the bailer, the ball valve falls down with the weight of the fluid above it and seals it from below. So again, not rocket science, but yeah, a clever idea, and it's time to do the kinds of things we want to do. So this is for, made the point that this is complicated analysis, but it's for fluid sitting on top of the water table. I guess the other point to make very briefly is that one way that you can get smear, not just in the column as it transited down to the water table, is by that puddle separating out and sitting on the top of the water table and spreading. Then seasonally, the water table rising or falling, I guess falling and then rising, and then as a result of that fall and then rise, it takes the smear that occurs when it drops, and then it takes that free product back above it again. So you end up with something at irreducible saturation of the non-wetting fluid actually existing below the water table, which it shouldn't have got to because it's actually lighter than water, but it's been carried down by the action of the water table. So that's for lighter than water fluids. You could imagine the same being the case for denser than water. You can use exactly the same ideas for ones that are denser than water. So here now, the water table would have been up here, or the top of the capillary, and the capillary fringe above it. And some DNAPLs gone down into here, into the section. And it's gone down, it's not stopped by the water table, it keeps on going. So it'll sit somewhere below the depth of here. So if you drill a well bore down to some depth, the height to which it rises is controlled by its behavior within the saturated zone, I guess. If you deepen that well bore, it will record a depth which is as deep as you want to drill the well bore, so long as there's enough volume of product that can come in to fill the well bore up to that particular depth. So here, the level of the well bore is here, the same in both cases. If you're taking this to be the depth of the material in situ, if there's a capillary barrier that sits here, even though the well bore is recording that here, that's not going to be a true depth. So I guess you have to be aware of that. The other thing is, if you want to sample this, and hot on the heels of our little video, is if you want to sample this and your baler is longer than this depth, then you're going to have to get the NAPL into there through the bottom and not through the top by decanting it over. And so bottom access balers with a ball valve in the bottom relate to that. If you look at the distribution of the phases within here, as you go up from here, DNAPL will come down as a plug. So this will be, if you like, why doesn't it want to draw? Because I guess it's on the side of the paper. So yeah, so this, if we're looking as to what this looks like, so this is our puddle going from a very high percentage here and getting less and less here. This would be our chimney, maybe with things cascading off it like we saw before, but this is now the saturation of the DNAPL as we go up here. This is below the water table. So this would be H2O. This would be DNAPL, I guess, all the way up here. And then above here, it would have left a smear. So this would be the smear, all the way down to here. And then it starts getting larger and larger saturations until it's at the full saturation it get to. So this is exactly the picture that we'd expect to see from the cartoons that we're drawing. And it's predicated on what the capillary pressure versus saturation curve would look like if we convert a capillary pressure into an elevation and actually it's not that. It has to be pre-multiplied by G, right? This is a unit weight, it has to be a unit weight. Units of stress and units of stress. So you might want to correct that earlier in our notes. So one final point which I will do for you. It's long, well, we've covered a lot of ground. G. So the final thing is that you'd expect that distribution in the subsurface, those saturation distributions, would be contingent on the capillary pressure versus saturation curves. So this is versus capillary pressure, but it also is a surrogate for depth. And so you could imagine two different capillary pressure curves. This one would be one where the non-aqueous phase liquid goes in at a very low bubbling pressure. And once it goes in, all the pores are the same size, so it completely saturates those. So this would be kind of a high porosity and high saturation in the system. And this high porosity would be arranged in terms of this capillary pressure versus saturation curve with depth. If you have a low porosity system, low porosity, and I guess small diameter pores, then it takes a larger entry pressure to break into the system. And once you break into that system, you have to progressively add more and more capillary pressure to be able to invade the porous medium with the DNAPL. And so you'd expect intrinsically from these capillary pressure versus saturation curves to look different, in that this has a large bank of NAPL here, representing this behavior here, because it gets down to this high saturation and then that high saturation continues. And this one to represent only getting to be high saturations once you get much deeper in depth. And so that's this one over here. So you have the puddle at the bottom sitting on top of a capillary barrier, and it's relatively thin puddle because of the shape of this capillary pressure versus saturation curve. This is NAPL, DNAPL of course. And above that it has a smear, which is these lower saturations mixed. And in the other case where you have much more open pore space, larger pore throats, is it has lots of NAPL included in here, so it can exist quite high up at relatively high saturations, and therefore this portion is much deeper in that particular case. And one final, I guess making the point about the bottom entry bailers, if you want to get access you have to have the NAPL coming through the bottom, and yeah, I don't want it to say anything about that. So if you're sampling, you might want to sample it using a bailer, depending on whether you have stuff floating on top of the water in the well or sinking down to the base of the well. You might want to use a bailer that allows fluid to decant into it from the top or to enter it from the bottom, weighted down to be able to sample it and bring it back to surface, and then to collect those samples to take back to the lab. And that's it for today. Yeah. So that's it for NAPLs. We'll do the same thing next time for talking about unsaturated flow, to be able to define, say, relationships which are empirical relationships which define how permeability and capillary behaviors are related in a relatively practical way from lots of measurements that have been made. So we'll talk about that next time.